All right, guys, in this video, we're just going to do a couple of examples. And don't forget, you've got your exam tomorrow. All right, so don't forget. Let's write this right here, even though I've sent you tons of reminders. Again, that is Thursday, May 7th. All right, so don't forget, 11:30 a.m. Okay, and then after tomorrow night, make sure you take a look at Canvas. Right, check Canvas. Right, check your grades, see where you stand, and decide if you're going to take the optional cumulative final. So you don't have to take it if you're happy with your grade after those 4 exams, but you certainly can to replace a previous exam score. Alrighty. So I want to take a look at a couple of structures. So for example, let's look at nitrogen trihydride, or we also know this as ammonia. And I'm going to take a minute to draw its Lewis structure. So counting up our valence electrons, we have 5 for nitrogen, plus 1 for hydrogen, and there's 3 hydrogens. So we have a total of 8 valence electrons in our picture. Nitrogen goes in the middle, it's our least abundant atom, and then I'm going to attach all other atoms with single bonds first, not going bond crazy until I see if single bonds work or they don't work. And then satisfying the octet rule for everybody except for hydrogen, because hydrogen follows the duet rule, can only have a single bond, which is 2 electrons next to it. Nitrogen has 2, 4, 6. So there is 8 for its octet, and then I'm going to recount and make sure I only used 8 total valence electrons in my picture. 2, 4, 6, 8. So this is my structure. Now, a couple of things about it. It's electronic geometry. So that's the arrangement of all atoms and lone pairs. So all groups on that nitrogen. Well, there is 3 hydrogen atoms, and then of course there is this lone pair, which is a 4th group. Okay, so again, we've got 4 groups. It's a very important number to count. Again, we're not counting lines, not counting bonds, just an atom or a lone pair on our nitrogen. So 4 groups is associated with the tetrahedral shape. There are lots of molecules with this tetrahedral electronic geometry. But what is the arrangement of just the atoms? Okay, those things that actually have taking up substantial space. Okay, and how are they influenced by that lone pair? Well, that lone pair is actually pushing those hydrogen atoms down into sort of this pyramid shape. So its molecular geometry is, some people just say pyramidal or trigonal pyramidal. Okay, not trigonal planar. It is not flat. It's not a flat triangle. Okay, so again, it's got this sort of pyramid shape to it. And if you sort of look at, there's that big electron cloud pushing those bonds down. This hydrogen is sticking out at you. This one's kind of going away from you, and this one's in the plane of the paper. And it does, in fact, look like a pyramid if I could draw better in 3D. Or I kind of think it looks like one of those little back massagers that you can massage your back with, but definitely that pyramid shape. All right, so let's practice hybridization. What is the hybridization of nitrogen if it were to hybridize? Okay, so 4 groups, remember, is associated with sp3 hybridization. And how many sigma bonds are in this molecule? Well, a sigma bond is the first connection between any 2 atoms. A sigma bond is not a single bond. A sigma bond can be found in a single bond. It can be found in our shorter, stronger double bond, and it can also be found in our shortest and strongest bond, a triple bond. Okay. Now, a double and a triple bond also have a second, or with our case of our triple, a second and third connection, where you have p orbitals interacting to form those pi bonds there. Okay, so just a little side note about different types of bonds there. And then if we wanted to think about our liquid ammonia in a bottle, what keeps it in that liquid state? What are those intermolecular attractions? Well, we need to figure out the polarity of NH3. So our NH bond, if you look at the difference in electronegativity between the two, nitrogen has a value of 3.0 and hydrogen is 2.1. Okay, so our change in electronegativity is a value of 0.9. Okay, so 0.4 or sorry, not 0.4, 0.5 or greater is a polar bond. 0.4 or less, a small difference, is a nonpolar bond. So nitrogen is a piggy, really tugging on the electrons in that bond, creating a dipole. So we have a dipole or a polar bond right here. But there are 1, 2, 3 polar bonds, so we have to look at our molecular shape. Okay, we've got that pyramid shape. And if you look at how things are pulling in our overall charges, well, nitrogen, being the piggy, is partially negative because he's really hogging those negative electrons. And then all your hydrogens then are electron deficient, kind of positive since the electrons are being pulled away from them. So if you notice, this creates a negative end and a positive side of the molecule. So we've got 3 polar bonds and they do not cancel. This is what we call a polar molecule. So all polar molecules have one side that's negative. Doesn't matter how many negatives there are, but all the negatives will be on one side and all the positives on another. All right, so this is a polar molecule. Now, what are the electrostatic attractions between a bunch or millions and billions of these ammonia molecules? Okay, so we just said NH3 is polar. Okay, so that means it's got dispersion because everything has dispersion. Okay, it also is capable of dipole-dipole attractions. Okay, because it is a polar molecule, but we need to ask ourselves the question, can it have hydrogen bonding? Well, the answer to that question is yes, it meets the requirements. Okay, we have a hydrogen atom bonded to nitrogen, oxygen, or fluorine. Okay, so this is our strongest intermolecular force that ammonia is using. Okay, it also has all of these other ones, but this is the strongest force that it has. Now, everybody has dispersion, all liquids and solids, okay, but this is also the only force that non-polar molecules have. Polar molecules have dispersion. They also have dipole-dipole. And then polar molecules that meet that certain requirement where you have hydrogen in a polar bond to nitrogen, oxygen, or fluorine, and they have to have a lone pair on them, have that super dipole-dipole called hydrogen bonding. Okay, so this is not the hydrogen bond. Our hydrogen bond, again, is an electrostatic attraction between different molecules. So we know that hydrogen is partially positive and nitrogen is partially negative because that was our piggy when we looked at our polarity. Now the actual hydrogen bond is this attraction between that negative and positive end right there. This right there is called the hydrogen bond. Okay, it's not a chemical bond, it's an electrostatic attraction. And that's what holds those ammonia molecules together in that liquid state. And it's these forces that we break up, say when this is vaporizing on a hot day and you smell those ammonia vapors. So when these attractive forces right here break, and this can transform from the liquid to the gaseous state. Alrighty, so I'm going to look at another molecule. Let's look at our sulfur trioxide. Okay. Now, counting up our valence electrons, we've got 6 for sulfur and 6 for oxygen. There's 3 of them. So that's a total of 24 valence electrons in our picture. Okay, sulfur's in the middle. Attach everybody with single bonds first. Satisfy the octet rule for every atom, which I'm doing. Can't forget sulfur. And then I'm going to recount and see how this looks. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So this is 26. This can't be our picture. If you use too many, that means there might be multiple bonding in there. So I'm going to add 1 double bond, not going bond crazy. And then I need to refix my octets. And then I'm going to double check how many I used. Okay, so now if I check 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this is 24. Okay. So this is 24 electrons. So that's good, but I need to check my formal charge. Okay. So the formal charge on my sulfur, I start with its valence number, which is 6, and then I count how many electrons belong to sulfur in this picture. Now, if you watch the previous video, we need to take half of each bond. So 1, 2, 3, 4. 6 minus 4 is a positive 2. Sad face. That's too much charge on our sulfur. And if we check our oxygens, we've got 6 minus 1, 2, 3, 4, 5, 6. Half of that bond would be 7. That would be a -1, okay? And so this oxygen's a -1, this oxygen's a -1, sulfur's a +2. If we check this oxygen, it's neutral. This is too much charge. The ones, +1s, -1s, zeros, those things are all fine, but this is not a good thing. So we need to draw our best structure. So what we can do then is we can move in. We want to bring that charge down and get it as close to 0, if not 0, would be best. Okay, I'm going to take this lone pair and shift it in. Okay, and then I'm also going to take this one in here and shift it in there. Okay, to bring that sulfur down to a 0 charge. Now, the central atom is not always 0, but if it can be, that's fantastic. So now we have this arrangement right here. We still have 24 electrons in our picture. We haven't changed that because you can't do that. Sulfur has an expanded octet, which it's okay because, again, it has to be in period 3 or below to have an expanded octet, so that's fine. And if we check our formal charge, it's now 0, so smiley face there. And all of our oxygens are also 0 as well. So this is our best arrangement here, okay? So a little bit onto our polarity. So here is our structure. If you check the polarity of the sulfur-oxygen bond, this is a polar bond. Okay, so I'm going to just draw my arrows pointing to the piggies. I want you on your own to take the difference in electronegativity. So we've got 3 polar bonds. So we need to look at the molecular geometry of this molecule. The molecular geometry is trigonal planar. It's a flat triangle. Planar means flat. Okay. This, if we look at our arrangement of our charges, looks a lot different than our ammonia did. Okay, I've got this in our trigonal planar shape, that flat triangle, okay, for our 3 groups, our 3 oxygen atoms. All of those oxygens are equal distance from each other, 120 degrees for all of those bond angles. Notice this looks way different than the NH3 that had one side negative and one side positive. Here, we've got negatives evenly spread out all over. This is a non-polar molecule because it's symmetrical. Okay, so again, this is symmetrical. Our polar bonds cancel. Okay, now in terms of intermolecular forces, nonpolar molecules only have dispersion. Okay, alrighty, and one last little example. Sometimes when we're looking at organic molecules, like a lot of those fuels we've looked at in combustion, like methane. What about things like propane? They have a lot of carbons in their structure, right? Carbon's always the central atom there. Butane has 4 carbons in it. Okay. And then what about something else called isobutane? We could look at this one. Kind of has a branched carbon coming off of one of them. Okay. Now looking at all these molecules, I don't need to draw their structures. These are all made up of carbon-carbon bonds and carbon-hydrogen bonds. And these are all nonpolar bonds. The difference in electronegativity is small, is 0 here, it's 0.4 here. Nobody is fighting over electrons, so these are all nonpolar bonds. It's just kind of nice to commit to memory. Okay, so all of these molecules, okay, they're all nonpolar then. If you have all nonpolar bonds, that makes you nonpolar molecules. Okay, that's why these things are a little more oily and whatnot. Okay, so again, this is methane, this is propane, this is butane, this is isobutane. Oh, did I add too many carbons? 1, 2, 3, 4, 5. Oops, sorry, that's isopentane. Let me get rid of one of those because I want to do that. There we go. Shame on me. 1, 2, 3, 4. 1, 2, 3, 4. Good. Okay. So now looking at these, since they're all nonpolar molecules, they all have dispersion that hold them together in their liquid state as a fuel. Okay, so that electrostatic force. Now, dispersion, the strength of it can be affected in two ways. So we first look at the overall size of the molecule, or its molar mass, its weight, its number of electrons. Okay, because that will really affect the overall strength. It will increase the strength. So that increases the strength of the dispersion. Okay, so looking at that, these ones with the 4 carbons are much bigger. Okay, and then this one with the 1 carbon is the smallest. So this CH4 then, being the smallest, okay, would have the weakest dispersion. Really easy to vaporize methane. Okay. Alrighty, now out of the other ones, the propane has 3 carbons. That would be a little bit stronger than the CH4's dispersion, but these two right here, they both have 4 carbons. So the second things to look at then would be at the branching. Okay. Branching decreases the strength because it's harder for the molecules to get closer together. So out of these two up here that are both 4 carbons, they have the same number of hydrogens, same number of carbons, which one's branched? So this one is what we call straight chain. I'm not going to use the word linear. It's not linear. These are all tetrahedral carbons, but it's just a straight backbone. They kind of zigzag like this. This one has a branch coming off. It's kind of like it's easy to stack logs. It's difficult to stack branches, like if you prune a tree. So those branches would make a humongous pile because they couldn't get close together because all of these darn twigs. Okay, so out of these two up here, right, this one would have stronger dispersion than this one right here. So let me write that down here. Our butanes, both forms of them, have the overall strongest, but this one would have a slightly stronger dispersion than our branched isobutane. It's got that twig coming up right there. Okay, so again, these ones have the strongest dispersion compared to the other two, 1 carbon and 3 carbon ones. But this one right here, being straight chained, has a much stronger dispersion than this one that also has 4 carbons and 10 hydrogens being branched. All right, guys, it's been fun. I will be talking to you soon through emails and announcements. And don't forget about your test tomorrow. All right, bye-bye.